going to be true of most problems. What if you can't make the bases the same? Then we're going to use another property, which says that if x is equal to y, then the log of x is equal to the log of y, right? It's kind of like x is equal to y, then x squared equals y squared. If you do the same thing to both sides, they still remain equal. So I'm going to take the log of both sides, or I could take the natural log of both sides. Now, for those of you who have books and are dealing with the book, they do some stuff a little differently. I'm not real happy while they do it, so I'm ignoring them. Because this is the way we do it most of the time. The further along in math you go, the more this is the way you're going to do it. And that's this. If I had 7 to the x is equal to 116, I cannot make the bases the same, so I take the log of 7 to the x is the log of 116. Properties of logs allows me to bring that exponent down. So x log of 7 is a log of 116. Log of 7 and log of 116 are just numbers. They're decimal numbers. So divide by log of 7. So you have a log of 116 divided by the log of 7. And then this is an exact answer. The minute I put it in my calculator, then I had to round so that x is going to be approximately 2.44. So here we go. 9 to the x equals 14. First thing I'm going to do is I'm going to take the log of the left-hand side. It's going to be, it doesn't matter what the original problem is. I take the log of the left, I take the log of the right, they're still the same. Properties of logarithms allows me to bring the x down in front. So x log of 9 equals the log of 14. Log of 9, log of 14 are just numbers. So divide both sides by the log of 9. X is the log of 14 over the log of 9. This is an exact answer. And by the way, if I want an approximate answer, and now I run out of space, x is approximately, and I already calculated it out, 1.2. I don't personally care if you give me exact answers or you give me approximate answers, as long as they're both right. Some of you might be more comfortable just putting in decimal numbers. Make the log of 9 a decimal, make the log of 14 a decimal, and then you're actually dealing with numbers instead of this thing that I'm calling a number. This symbol, it's really a symbol. Again, I can't make the 2 and a 5 to be the same base, so I'm going to take the log of both sides. So the log of 2 to the x plus 3 equals the log of 5. See, I use log base 10 because it's on my calculator. I could use natural log as well, and there's going to be times we're going to use natural log because it will be of much benefit to us. Now, what I want you to notice is this. X plus 3 is a grouping. So when I bring it down, it is a grouping. So bring the exponent down. I bring a set of parentheses down. What's in the parentheses is x plus 3. Now, I can do one of two things. In college algebra, we tend to clear the parentheses, multiply it through. But since this is a multiplication, I can just divide both sides by log of 2, which is what your book does, by the way. So x plus 3 equals log of 5 divided by log of 2. That's just a decimal number. So that x equals log of 5 divided by log of 2, subtract 3. And this gives me an approximation of negative 0.678. That's convenient. So again, this is an exact answer, and this is an approximate answer. This is where you're going to have to be very careful, because when I go to take the log of 5, I need to make sure that I close that off before I do the log of 2, and I have to make sure I close that off, and then I can subtract 3. If I don't have the right parentheses in, I'm going to get the wrong answers. Personally, what I probably would do is I would do that first and then subtract 3. Oops, maybe. It didn't like what I do. Subtract 3. And then you would end up in the same place. Yeah, either way. And like I said, this would be a perfectly good answer. If you have a book, you take a look at it. That's essentially what the book does in terms of their answer.